Have you ever wished you had a real-life invisibility cloak, just like in the movies? While that might still be science fiction, scientists are working on something almost as magical called metamaterials. These are not materials you find in nature like wood or stone. Instead, they are engineered materials designed with tiny repeating patterns that are even smaller than a wavelength of light. This special structure gives them amazing abilities. They can bend light in ways that normal materials cannot, which is why scientists are so excited about them. These materials get their powers not from what they are made of, but from how they are built, piece by tiny piece. Imagine a Lego castle. The castle's shape and strength come from how you arrange the individual Lego bricks, not just from the plastic they are made of. Metamaterials work in a very similar way, but on a microscopic scale. Scientists carefully design and build these tiny structures to control light, sound, or other forms of energy. This allows them to create materials with properties that seem impossible, like bending light backward or absorbing all sound. It is a new frontier in science where we are not just discovering materials but inventing them with specific superpowers in mind. One of the most exciting types of these special materials is called a photonic metamaterial. The word photonic has to do with photons, which are the tiny particles that make up light. So, photonic metamaterials are specifically designed to control light. Think about a normal window. It lets light pass through in a straight line, but a window made from a photonic metamaterial could do much more. It could be designed to let in sunlight for warmth in the winter, but block it to keep things cool in the summer. It could even be made to focus light like a lens or change its color on command. This ability to manipulate light opens up a world of possibilities that we are just beginning to explore. Normal materials like glass or plastic have their properties set in stone. A glass lens will always be a lens with the same focus. But what if we could have materials that change their properties whenever we want? This is where nanomechanical photonic metamaterials come into play. They combine the light-bending magic of metamaterials with tiny moving parts, giving us materials that can adapt and transform right before our eyes. This is the next giant leap in how we build the tools and technologies of the future. So, how do we make these amazing materials change? The secret lies in something called nanomechanical parts. The word nano means incredibly small, so small you would need a powerful microscope just to see one. Mechanical means it has moving parts. These materials are built with tiny, movable films called nanomembranes. Imagine a drum skin that is thousands of times thinner than a single human hair. These nanomembranes are stretched out in a precise pattern, and their job is to move just a little bit to change how the material interacts with light. These super thin films are often made from materials you might already know, but in a very special form. Scientists might use silicon nitride, which is a very strong and stable ceramic material, or sometimes even thin layers of metal like gold or aluminum. The key is that these materials can be made into membranes that are both flexible and strong. When they are arranged in a grid, they create a surface that looks perfectly flat, but is actually full of tiny individual parts that can move up and down or bend and flex. This movement is the key to their power. When light hits this surface, its path is determined by the exact shape and position of all these tiny nanomembranes. If the membranes are all flat and in a perfect line, the light might just reflect off like a mirror. But if some membranes are bent upward while others are pushed downward, the surface becomes bumpy on a nanoscale. This carefully controlled bumpiness can steer light in a new direction, filter out certain colors, or even focus light to a single point, just like a camera lens. The material's optical property, how it affects light, is directly linked to the physical shape of its surface. Think of it like the surface of a lake. When the water is perfectly still, it reflects the sky clearly. But when wind creates ripples and waves, the reflection becomes distorted and scattered. Nanomechanical metamaterials work in a similar way, but instead of wind, we use other forces to create precise ripples on demand. By controlling the shape of each tiny membrane, we gain complete control over the light that touches it. This allows us to build dynamic, tunable devices that can adapt to different situations, all without any large, bulky moving parts. Controlling these tiny nanomembranes requires a special kind of power, but not the kind that comes from a wall outlet. Scientists have developed several clever ways to make these membranes move with incredible precision. One of the most common methods uses electricity. This is called electrostatic control. Imagine holding two magnets near each other. They either pull together or push apart. By applying a small electric voltage to the nanomembrane and a surface below it, scientists can create a similar force that pulls the membrane down or allows it to spring back up, changing its shape instantly. Another amazing way to control these materials is with heat, which is known as thermal control. Some materials are designed to expand or bend when they get warmer. By gently heating a specific part of the metamaterial with a tiny focused beam of light or a small electrical current, scientists can make the nanomembranes in that area change shape. This method is like watching a flower open its petals in the morning sun. A small change in temperature can cause a significant and predictable change in the material's structure, which in turn changes how it controls light passing through it. We can also use magnets to move the membranes. For this to work, the nanomembranes are built with a tiny amount of magnetic material in them. When an external magnetic field is applied, it can pull or push on these membranes, causing them to flex and bend. This is similar to how you can move a paperclip around on a table by holding a magnet underneath it. This magnetic control allows for fast and precise movements without needing any physical wires connected directly to the moving parts, which is a huge advantage for creating clean and simple devices. Finally, we can even use light to control light. This is called optical control. Some materials are designed to absorb light and convert that energy into a tiny force that pushes or pulls on the nanomembrane. So, by shining a control laser onto the metamaterial, you can change its shape and, as a result, alter how it affects another beam of light. This is truly futuristic technology, where one beam of light acts as a remote control for another. All these methods give us a powerful toolkit to design smart materials that can change their function in the blink of an eye. These incredible nanomechanical photonic metamaterials are not just a cool science experiment, they are paving the way for real-world technologies that could change our daily lives. Think about the camera in your phone. To focus, it uses a small motor to physically move a glass lens back and forth. This uses battery power and takes up space. Now, imagine a camera lens made from a metamaterial. It would have no moving parts, just a flat surface that could change its focus instantly by applying a tiny bit of electricity. This would make cameras smaller, faster, and much more energy efficient. This technology could also revolutionize the screens we look at every day. Instead of pixels that create light, we could have screens made of metamaterials that reflect ambient light and control which colors we see. This would be like an e-reader, such as a Kindle, but with full, vibrant color and video capabilities. Such a display would use almost no power compared to today's screens, meaning your phone or tablet battery could last for weeks instead of just a day. It would also be much easier on your eyes, as it would look more like ink on paper than a bright light shining at you. Beyond phones and cameras, these materials could lead to amazing new sensors. For example, a tiny, low-cost sensor could be created to detect specific chemicals or viruses in the air or in a drop of water. When the target molecule touches the metamaterial's surface, it would cause a tiny change in the shape of the nanomembranes, which would alter the light reflecting off it. A simple detector could then read this change and sound an alarm. These sensors could be used in hospitals for instant medical diagnoses or in cities to monitor air quality with incredible accuracy. The future powered by nanomechanical photonic metamaterials is one where technology is smaller, smarter, and more seamlessly integrated into our world. From glasses that can instantly change focus from near to far, to windows that intelligently manage a room's temperature, the applications are almost limitless. We are learning to speak the language of light, and by building materials that can control it with such precision, we are unlocking a new era of innovation. The tiny moving parts of today are setting the stage for the giant technological leaps of tomorrow.